want an off-the-shelf language model. What is our company's refund policy for enterprise clients? Instantly, the model generates a detailed, authoritative response. But there is a massive problem. That policy doesn't actually exist. The model completely fabricated it. You've just encountered a hallucination. The model generated this false data because it lacks access to your private files. It was trained on the public internet up to a specific cutoff date, and its neural network weights are frozen. When asked about unseen internal documents, it relies on generalized training to predict the next most likely word, rather than looking up facts. Scaling up the model size will not fix this inherent blindness. For mission-critical engineering, the system needs a concrete mechanism to feed the model exact real-time facts instead of relying on its ability to guess. Retrieval-Augmented Generation, or RAG, splits the process into two distinct steps. In the retrieve phase, the system searches your private database, pulling documents containing the answer. Then, the generate phase bundles your question with those facts, instructing the language model to synthesize an answer. By separating these actions, you change the language model from a student taking a closed-book test from memory into one taking an open-book test with the reference material right in front of them. The result is a verifiable answer grounded in truth. But building a dedicated retrieval pipeline takes effort. Why not just fine-tune an existing model directly on your company data, or simply paste all your documents into a massive context window? This comparison matrix highlights the technical friction points that stop those approaches from scaling. Whether it's high GPU requirements or slow inference times, these constraints act as three distinct walls: cost, latency, and freshness that block production-ready AI. Looking at the fine-tuning column, you see that when you bake private documents directly into a model's weights, that knowledge becomes a static, frozen blob. If a policy changes tomorrow, you have to retrain the model to update it. Furthermore, because all the data is assimilated into one structure, you cannot filter access. The model could easily leak confidential HR or executive data to an unauthorized employee. If you try to use massive context windows, pasting thousands of pages into every single prompt, you hit compute limits. Stuffing a wall of text into every API call forces you to pay a high cost per query for mostly irrelevant documents, and processing that much data slows inference to a crawl. The RAG column shows how this architecture sidesteps all three walls. Because it only extracts the top few relevant paragraphs, it remains cheap and fast. Updating facts is as simple as updating a database row, and you can apply standard security permissions at the retrieval step so users only interact with data they are authorized to see. To execute this, a RAG architecture operates on two distinct asynchronous data pipelines: the ingest pipeline, which you build once to process your documents, and the query pipeline, which runs dynamically every time a user asks a question. The ingest pipeline starts with your raw private documents. Language models and retrieval systems have strict context limits, so the system breaks these massive files down into smaller, manageable units called chunks. Next, an embedding model translates the text of each chunk into a high-dimensional mathematical array, known as a vector. This captures the underlying semantic meaning of the words. These vectors are then stored in a specialized vector database, which is optimized to index and search numerical arrays. When a user eventually submits a prompt, the query pipeline takes over. It translates the user's question into a vector using the exact same embedding model and runs a semantic search against the vector database. By calculating the mathematical distance between vectors, it identifies and extracts the chunks with the closest meaning. Finally, the pipeline takes the user's original question, packages it alongside those closely matched chunks, and hands the entire bundle to the language model to synthesize the final, grounded answer. By decoupling the reasoning logic of the language model from the memory storage in your vector database, you create a system that is secure, highly scalable, and dynamic. While this architecture provides a clear path to production AI, it introduces a severe bottleneck. Your system is only ever as good as the specific chunks it manages to retrieve. If your semantic search pulls paragraphs that are irrelevant, outdated, or improperly formatted, the language model will use them anyway. It will confidently generate a highly articulate but entirely incorrect answer based on flawed evidence. Controlling this retrieval quality requires mastering three foundational engineering choices: how you configure your chunking strategy, the specific embedding model you select, and the vector database you deploy. Dialing in those three variables separates a brittle prototype from a robust production-grade application. We will break down exactly how to engineer those components in the next chapter. How we chunk our text, which embedding model we use to translate it, and the vector database we select to store and search it. The first step is chunking. This is where we break a long document down into smaller pieces. It is the exact moment a distinct fact is isolated. Cut the text correctly and you preserve the semantic meaning. Cut it poorly and the meaning is destroyed before the AI even gets a chance to read it. This diagram illustrates how naive splits sever a thought. A rule goes into chunk A, but its critical exception is pushed into chunk B. The system only retrieves the first chunk. The AI reads an absolute rule and generates a confidently wrong answer. The chunking ladder fixes this problem. Moving up from a fixed size split increases text fidelity. The second tier, recursive chunking, looks for natural breaks. It splits at paragraphs first, then steps down to sentence boundaries, using a hard cut only as a last resort. We control boundaries using two dials, maximum tokens and token overlap. A standard start is a 1,000 token limit with a 200 token overlap. This overlap acts as a bridge, duplicating edge tokens so the severed exception merges right back with the main rule. Properly tuned chunk boundaries function as a defense mechanism. They guarantee that our text is contextually whole, with facts fully intact, before the next stage of the pipeline processes it. Once the text is safely chunked, it moves to the embedding model. This model translates human language into dense vectors, long arrays of numbers that map the text into a mathematical space, where we can measure similarities. This chart breaks down embedding model trade-offs. The first priority is domain fit. A generalized model might top public benchmarks, but processing complex medical journals or proprietary codebases requires a model trained specifically on that domain. Next is the dimension count. Embedding models map text across hundreds or thousands of mathematical dimensions. More dimensions capture higher nuance, but precision carries a linear cost. As dimension count rises, you consume more storage, compute power, and incur higher latency. We also face hard architectural constraints. Many models cap around 8,000 tokens, which dictates our maximum chunk size. We also must decide who runs the hardware, routing text through a proprietary API or self-hosting open-source models for total privacy. But regardless of which model you choose, the architecture demands one absolute rule. You must embed your source documents and your user queries using the exact same model. If you mix them, the coordinates don't align, and the space becomes meaningless. The final stage is the vector database. This is the engine that actually stores our generated vectors and runs the similarity search when a query comes in. This matrix outlines the four primary axes we use to evaluate our options. The most critical choice is the index structure. Exact linear search guarantees perfect accuracy by comparing every vector, but is too slow. Instead, we gain massive speed using an approximate nearest neighbor index, ANN, which navigates a layered graph to find matches in milliseconds. We also have to configure for scale. We can run an embedded library directly on a single machine for smaller workloads, or deploy a distributed, fully managed cluster when we need to support millions of vectors and high concurrent traffic. Quadrant 3 highlights metadata filtering. This operates outside of the vector math, acting strictly as an access control mechanism. By attaching permission tags directly to the vectors, we ensure that a user querying the database only retrieves documents they are explicitly authorized to see. Finally, we introduce hybrid search as our ultimate quality lever. Dense vectors excel at broad concepts, but struggle with exact matches. Hybrid search combines semantic vectors with sparse exact keyword matching to catch highly specific names, product codes, and typos. These database trade-offs dictate the reality of the system. They determine whether the rich, nuanced vectors we generated can actually be queried with the speed, latency, and strict security constraints demanded by a modern enterprise. Our pipeline is now fully formed. Carefully tuned chunks guard the original context. The embedding model maps the domain vocabulary into a mathematical space, and the database executes the search geometry. If you execute this architecture on a laptop, indexing a few thousand documents for a single user, it operates flawlessly. But point that identical architecture at millions of documents and open the gates to thousands of concurrent users, and the system buckles. The sheer volume of data and traffic exposes the physical limits of memory and compute bandwidth. Engineer those three well: chunking, embeddings, the database, and you have a RAG stack box on your laptop over a few thousand documents. Point it at millions of documents and thousands of users at once, and every choice is tested again. Where RAG breaks at scale and how to fix it is next. This is neuralsca. Neurals.ca.